We know that all matter is made of atoms. The ancient Greeks first thought of it. Then in 1800, John Dalton reintroduced the idea. But what are atoms made of? Here we see the structure of the atom showing the three subatomic particles, the proton, neutron and electron. As you can see, the proton and neutron are in the centre part of the atom, which is called the nucleus. They both have a relative mass of 1, but the proton is positively charged, whereas the neutron is neutral, as its name suggests. The electron has a very, very tiny mass. At GCSE, we just refer to it as being very tiny, although we can measure it. The charge on the electron is -1, so it's exactly opposite to the proton. The electron exists around the outside of the atom. It exists as a cloud of electrons. The periodic table tells us how many of each of those subatomic particles are found in the nucleus of any one element's atom. This is fluorine, for example. The atomic number is the smaller number, that's the one at the bottom, and it tells us the number of protons. So fluorine has 9 protons in its nucleus. The atomic mass is always the larger number because it's the number of protons plus the number of neutrons. So if I've got 9 protons and I take that away from 19, I must have 10 neutrons in the nucleus of fluorine. So what are protons, neutrons and electrons made of? This is where we introduce something called the Standard Model. This lists all the fundamental particles. There are 2 main families of particle, the quarks and the leptons. So let's start with the quarks. Quarks don't exist on their own, they always bond with other quarks to make larger particles. There are 3 generations of quark, getting heavier and less stable as you go down the generations. In each generation you can see 2 partner particles, up-down, charm-strange and top-bottom. The up, charm and top quarks all have a charge of +2/3 e, where e is the charge on an electron. The down, strange and bottom quarks all have a charge of -1/3 of e. If we have 2 up quarks and a down quark, up, up, down, the total charge comes out at +1, which is the same as a proton. So a proton is made of up, up, down quarks. Now let's return to the Standard Model and look to the other part of that diagram where we've got the leptons. Unlike quarks, leptons never join with other particles, they're always alone. We've already met the electron, obviously. Leptons also have 3 generations, the electron, muon and tau particles. These also get heavier as you go down the generations. Like quarks, leptons also have partner particles. They're called the neutrinos. We have the electron neutrino, the muon neutrino, and the tau neutrino. The electron, muon and tau particles all have a charge of -1e. We already know that the electron has a charge of -1. Neutrinos have no charge, as their name suggests, they're neutral. Neutrinos are odd because they have no mass either. Having no charge and no mass makes them really difficult to detect. So we've covered all of the fundamental particles of matter. We now know that electrons are leptons, so they can't be broken down into anything smaller. We also now know that protons and neutrons are both made of quarks, and we know that they are made of a combination of up and down quarks. The bit on the right-hand side, the force carriers, we will look at in a moment, but before that, we have to consider so for each matter particle, there exists an antimatter version. That means that there are 12 particles of matter and 12 antimatter particles. For example, you could have an anti-electron, you could have an anti-charm quark, you could have an anti-muon neutrino, and so on. The definition of an antimatter particle is that it has the same mass but opposite charge of its matter counterpart. For example, the electron has a mass of 9.1 times 10 to the minus 31 kilograms. The anti-electron has exactly the same mass. The electron has a charge of minus 1.6 times 10 to the minus 19 coulombs, or minus 1 times E. The anti-electron has the same charge but positive. So what happens when a particle meets its antimatter counterpart? Well, the answer is they annihilate and their mass is turned into energy. And we can calculate how much energy that is using Einstein's equation E equals mc squared. E is the energy, m is the mass, and c is the speed of light, which is 300 million meters per second. Einstein's equation tells us that as well as a particle and antiparticle pair annihilating, which you can see in the diagram on the top right, if you have the right amount of energy, you can also make a particle-antiparticle pair, which we see in the bottom diagram. To get the right amount of energy, therefore, you can appear to make matter out of nothing, and that's because we need to see matter as a type of energy. So what we might ask from this is this how come we've got matter after the Big Bang? We know that the Big Bang was just a large ball of energy, and the universe then expanded and cooled down. This means that that energy could then turn into particle and antiparticle pairs, which then make all the matter that we see in the universe today. So if some of the energy from the Big Bang became particle and antiparticle pairs, then the big question is, where is all the antimatter today? Logically, there should be 50% matter and 50% antimatter left in the universe. And yet we know that's not true. None of us wander around each day worrying about bumping into antimatter or having parts of ourselves annihilated. So clearly, certainly in the universe that we can observe, it's almost entirely made up of matter. And this is one of the big questions we're still asking ourselves. Finally, we'll look at the force carrier particles, and they're shown over on the right-hand side of the diagram. There are 4 fundamental forces that work in the universe, and they are shown below, and that's gravity, electromagnetism, and the strong and weak nuclear forces. Now, we know quite a bit about gravity. It's the first one we learn about in school, and it's the one that we've probably known about for the longest, thinking back to people like Galileo and Newton. It's also the weakest force, which sometimes seems surprising to us. It certainly works over a very long range. It has an infinite range, but it is the weakest of the 4 forces. Electromagnetism also works over an infinite range, but is much, much stronger. The strong and weak nuclear forces, as their name suggests, work over much smaller distances. So even though they're both stronger than gravity, they work within the nucleus of an atom. So they're fundamental to us understanding how matter comes together. Forces are exerted when force particles, also called exchange particles, are exchanged between matter particles. Now, it's not an easy concept to grasp at GCSE. So what I'd like you to understand is that there are 4 fundamental forces and 4 fundamental particles that carry those forces. And the diagram on the left, I think, makes it a little bit clearer. I'm going to start at the bottom with the strong force that binds quarks together. Now, the particle that carries the strong force is called the gluon. So if we think about gluons gluing quarks together, then that is the force that keeps the quarks together in the particles like protons and neutrons that we've looked at in this presentation. As you can see, it has a very short range because it's just acting within the nucleus. If we go up to the next level, then we've got electromagnetism, which acts between electrically charged particles, and this force is carried by the photon. Now, photon is Greek for light, so photons are particles of light. And this is an idea we start to look at in more depth as we go between GCSE and then up to A level. But electromagnetism we do look at in year 11, so this becomes clearer as you go through the course. Going up to the next one, we've got weak force, which governs particle decay, but also radioactive decay, which we look at in Unit 4 in Year 10. Now, the weak force is carried by the W and Z bosons. Like the strong force, it has a short range because it's acting within the nucleus. It's what enables the particles in the nucleus to decay and change, which again we look at in Unit 4. Finally, we're going to look at gravity. It's tempting to see gravity as something we understand well because we've been aware of it for a long time, but actually it's the force we know the least about. We do know that gravity acts on anything which has mass, so masses attract each other. Now, it says over here that the particle is called a graviton, and I put it in those little commas because we don't actually know that for certain. No one's actually found or discovered the graviton, whereas we have observed and discovered all the other particles. Gravity is a bit of an odd one out here. It doesn't quite fit in the standard model properly. It's got an infinite range, but it's a very weak force. It only attracts, it doesn't repel. So at the moment, we don't entirely understand how gravity would work with the standard model here. And in fact, this is a question that scientists are still trying to answer today. So you might wonder how we know all this. Well, we go back to our old friend Einstein's equation, E = mc². We smash particle-antiparticle pairs together, they annihilate, and this releases energy, which can then go on to form new particle-antiparticle pairs, which we detect and study. Now, we do this in particle accelerators, and on the right I've put some pictures of perhaps one of the most famous ones in the world, which is CERN in Switzerland. If you look at the top right, it shows a large circle. This shows the pathway of the particle accelerator. Although it's in Switzerland, it actually passes under the border into France because it's so large. It takes up so much electricity they can only run it in summer because in winter the surrounding villages need it to power their homes. Now what we do is we go around in a circle because we can get those particles close to the speed of light, so they have lots of kinetic energy when they finally collide. The top left actually shows the tunnel that the particles go through. It's actually quite small, but it's really dangerous because once they get going up to those really high speeds, it gives off lots of gamma radiation. So it's also buried very deep in the ground to make sure that it's safe. The last picture right on the bottom shows one of the detectors. You can just about see the people in the picture, so it gives you an idea how enormous the detectors are, even compared to that tiny tube that you can see that the particles will pass through. We're still running CERN today, because although we know a lot about the standard model, there's still a lot more that we can learn. That's it for our whistle-stop tour of particle physics. Here are some links you might find useful. I'll also make sure that I put them in the blurb underneath the video in YouTube.